And since you've seen it from both sides, how is that projector? Is it about the same off, say, a desktop, laptop?
Yeah, it's fun.
That's good to hear. It'd be kind of rough if it's only good through a computer screen.
Right. I'm thinking of it like I'm watching it from a big screen.
Yeah.
The movie theater.
Well, I think it's official, folks. We're now in week 5. Oh, didn't mean to hide it. We didn't get through it that fast. But the interesting thing about week 5 is it is a 16-week semester, but the 16th week is finals week. That's not an instructional week at all. So after this week is over, we're 1/3 of the way done through all the actual course content we're going to get through. So definitely making our way through. Big announcements is that we got through our first exam. Congratulations on getting through that, folks. I think it was a difficult one to get set up, but once it was set up, it kind of just worked. So I appreciate everyone's patience, especially with some of the roundabout testing centers you might have gone to. You should check your ISU email if you haven't already. I emailed you directly to that address, your exam one. And if you don't see it anywhere, just send me an email at any point. I'm happy to just resend it to you. For some really basic statistics, the average grade came out to 82.6%, and 6 people in the class had a perfect score of 100%. So, congratulations to those folks. The exam wasn't meant to be tough. Pretty much, if you've gotten through the homework content that it was over, then it was kind of smooth sailing on that exam. Well, any questions at all, folks, to start us out before we go back to 5.4? Okay, if you're curious about the exam, if questions do come up, don't hesitate to email me. And you can also check out this document here for the solutions on that exam. And as far as the modules, I guess they call these, or yeah, I think it's called modules on Canvas, still learning the lingo. The way these are all going to work is pretty much just a redo of what we did on the exam or week 1, getting into exam 1. Week 5 is going to be an ordinary instructional week. So is week 6, week 7. Then in week 8, we'll have our midterm week. Midterm week doesn't mean the exam 2 is going to be like a long exam or anything. It's going to be another 50-minute exam. As we get at the end of week 6, that's when I'm going to fill out this information here for the exact coverage on exam 2, review problems that you'll be interested in taking a look into, and that kind of stuff. Also, going from Friday of week 6 to Monday of week 7, that's when I'm going to get the second round of all information sent to you for the various testing centers. So pretty much it's just a repeat of everything we've done over and over again until we get to finals week. So we left off on, we basically finished section 5.2. We just didn't want to take another 2 or 3 minutes to finish off the last part of the last example of section 5.4. But we're officially finishing it today, so the due date is a week away from today. And this is where we left off on. We're dealing with right triangle trigonometry. The major mnemonic to help us organize information is the SOHCAHTOA mnemonic. So in this right triangle right here, we decide to use the TOA part of SOHCAHTOA. It tells us that tangent at 60 degrees is going to be O for opposite divided by A for adjacent. So at the 60 degrees, I'm on the wrong spot over here, we took 10 divided by A. That's how this problem started out. Tangent pi over 3 we found is just root 3. That allows us to form an equation from which we solve for A. Then we rationalized it. And just another reminder, if you write in your answer like this, it's totally fine. If you leave your answer like this in the non-rationalized form, that's equally good. There's some contexts where it's even better to leave A equals 10 over root 3. Say you're doing more algebra on this. This is algebraically more simplified than this is down here, even though we call it simplified because it's rationalized. Last thing we had to do to fully solve this problem was solve for all the unknown sides. So C was just left hanging out. We needed to finish up this problem, go C squared equals A squared plus B squared. Forgetting how the color coding went. So then just substitute in the information we have. C squared equals A squared. Now here you do have an opportunity. You could square this number. It works out. It's more steps though. Or you can use the pre-rationalized form, 10 over root 3. That's easier to square. So that's probably what I would do on this one. Plus B squared is just squaring 100. Or excuse me, 10 to get 100. So on the next line, C squared. In the numerator, we're going to get 100. The square of the square root of 3 is just 3. Plus 100 again, then we're dealing with fractions, so let's put this over 3. 3 goes into 300, 100 many times, so now this is C squared equals 400 thirds. After combining the fractions, take square roots. And C is going to be, that one's a perfect square, 20 by 20 is 400. So square root of 400 is 20, and the denominator is 3. Then this is a totally acceptable answer, but I often, not always, there's a couple times I skip this, but I often take this additional step to say, this is 20 over root 3 times root 3 over root 3 to rationalize the denominator. So this becomes 20 root 3 over 3. So we've got it, folks. The unknown sides are this part right here. I'll box it out because it's like a algebra cloud of stuff that we ended up with. And the side length for A is the 20 root 3 over 3. Well, any questions, folks, with the conclusion on this one? Okay, see these examples here when you're starting off your assignment 5.4. There's some pretty tricky problems. And I think one tricky problem just out of nowhere, almost unfortunately, is problem number 11, which is like the second problem you would do in that whole homework set. So just for a quick hint, I should say on what this hint is relative to, hint on number 11, there's really two things you can try. They tell us that sine B equals 1/2. And if you've tried this problem already, you might have noticed that's not really convenient information. That's a tough set of information to give us. So one thing you can try is the following. Method 1, use the Pythagorean identity. This is fantastic on this problem. It's probably what the author had in mind. Use cosine squared B plus sine squared B equals 1 to solve for cosine B. Then suddenly it becomes a problem that we can really get started. It's like the second example on these notes. Another method too, if you really scratch your head at this problem and you tried this out and you felt like it was a good idea, good on you. This is probably the cleanest way to solve this one. If sine B equals 1/2, then because B is an acute angle between 0 and 90 degrees, this means B is going to be equal to pi over 6. And that's really good information for us. If we know B is equal to pi over 6, then the angle A is pi over 3. Those deserve exclamation marks. That's because pi over 6 is 30 degrees, pi over 3 is 60 degrees, and in a right triangle, these are complementary angles. They have to add up to 90 degrees. So using this information right here, you skip the algebra up here. It's a little bit tricky, but the idea was sine of pi over 6 is indeed 1/2. So we're just solving a trigonometric equation to get the angle B, which then gives you the angle A. Much more to work on than the minimal information they gave us in this problem. So take a look at this hint if you get stuck. And if you're still stuck, don't hesitate to email. Turns out problem number 11 is probably the hardest one in this homework set, which is kind of backwards in a certain sense. Usually nicer homework sets kind of like build in difficulty. They don't just start off with one of the hardest ones in there. But The next section we're going to get into is finally turning over to chapter 6. So we're finally done with the chapter 5. Any last questions or thoughts before we close out these notes?
Yeah, I wanted to, on method 1, I could not figure that out for the life of me. I kept getting the wrong answers. And so I kind of bumbled into method 2 accidentally and found that easier. But I don't see how to do it via method 1.
Yeah, let's take a closer look at that. Thanks for asking about it. So if we're going to use method 1, what we're doing is putting in a value here for sine of b. So this would turn into cosine squared of b plus the square of sine. Sine was a half, was what was given to us in this problem, equals 1/2. So then we would get cosine squared of b is 1, well, let me try again. That's a plus sign there, plus 1/4 equals a half we can convert into 2/4. And then cosine squared of b would be equal to 3/4, and we're almost there. We take the square root of both sides, and if you're thinking there's going to be a plus and minus when you take that square root, good on you. It's still the safe thing to do algebraically. But we just happen to know something about the angle B. It's an acute angle, so it's in quadrant 1 where it terminates. So even though plus and minus is the right thought, turns out this is just strictly positive. So cosine B would come out as positive root 3 divided by 2. Does that make sense on getting that cosine value?
Yeah, that does. I think what I did was I didn't do the plus minus value and it just kept throwing me off.
I gotcha. Yeah. Here we're just lucky it's got to be positive on this one. And just another thought on consistency with this. When we said b is pi over 6, we can definitely say that cosine b is now cosine pi over 6, which is definitely root 3 over 2. So it's kind of cool to see that it's consistent. Either way we're going to go at this, we're going to get that cosine b value. Well, any last other questions at the moment, folks? Yeah.
Get 1/2 at the top. Cosine b, so cosine squared b plus 1/2 squared equals 1/2. Where did you get that second one?
That's a great question. So this 1/2, let me look at that again. That looks like a mistake in my algebra. I should have said equals 1, right? So if that was a 1, and how did this even work out? I think my mind just kind of mentally forced this to work out. That should have been a 1. And so then when I came over here, find the right common denominator, it's 4 over 4. Then subtract a 4th from both sides. And that's how you get to the 3/4. That's where it finally resolved correctly. Yeah, good eye on spotting that. It should definitely be equal to 1, not a half. That was weird algebra. I think I just got distracted by this, and then my mind just forced it to work, getting to what I was expecting to get. Weird. Good eye on that one. Other questions so far? Glad we got that correction there in the notes. Okay, well, let's switch gears then. If you think back to pre-calculus 1, other algebra courses, this is kind of following the same sort of order of topics. You define a new function. Maybe it's the logarithm function or the exponential function. You look into some properties of that function, and then you want to know what are the graphs. That's chapter 6. You want to know how to solve the equations. That's chapter 7. And then additional applications. That's going to be chapter 8. So kind of the same thing you might have done with exponential functions or logarithmic functions. Before we dive into the graphs, you might have noticed there's a lot of extra documents here. We'll take a look into each one of these in turn. Summary of plotting techniques is an overall summary document. So it might not be too useful right now, but when we're at the end of section 6.1, starting section 6.2, it becomes a little bit more relevant. Transformation of graphs is just review material from pre-calculus 1, sometimes called college algebra. And it's just a reminder for if we transform the graph of, say, a logarithm by, say, adding c, The new point is just c that's up and other so-called things. We want to move the graph of a logarithm to the right. We put minus c in natural log x minus c, and a bunch of other things that we'll review as we go. But the ultimate goal is to not cite this document directly. We're going to see how do these ideas combine, Mike? How do these ideas combine into an overall basic set of techniques? That's a summary of plotting methods. So we'll connect the dots here just for the sake of reviewing college algebra. Let me make this slightly easier to work with. So when we take another look at it, it's available. And next thing we're going to look into is just a quick graphic. This one's kind of a fun one from wikipedia.com of all places. But if we're taking the definition of the unit circle trigonometry, and now we're going to plot things, it means everything feels a little bit different. On one hand, you had this graph, where we took an x-coordinate and a y-coordinate. The x-coordinate is cosine x. The y-coordinate is, hang on, let me fix that. Not cosine x, but cosine of an angle theta, where this is the measurement theta in the diagram. Y is sine theta. But now when we go to actually plot cosine or sine, we're going to be plotting in the x, y equals cosine x, or y equals sine x plane. So in other words, we're making a switch right here. It's a change of perspective. Angle theta could have been any real number. And up here in the xy plane, that's what theta is. We're just used to plotting an xy plane, and so we're going to carry that information over. So if I go to plot cosine x, I'm now thinking of x as just the input to the angle. Whereas over here, if you're defining cosine theta, sine theta, x is the first coordinate, cosine, y is the second coordinate, sine. So two totally different perspectives. Here's what the plot would look like. And we'll take a really closer look at this, but this is just a fun way to see it, connecting the unit circle. So here's the unit circle just winding its way around by where the red dot is. We said that cosine is the x-coordinate, and that's what this vertical line is. It's representing any x-coordinate on the cosine function. But it's plotting here in the xy plane, just a curve that repeats itself. It has a definite boundedness to it. It never got bigger than +1 or -1. Here it's at the +1 end. Here, now it's at the -1 end. And sine looks like the same thing. It's just taking all the y coordinates out of there. Same idea, it's bounded as well. Positive value is at +1. Its minimum value is down here at -1 when we get to 3 pi over 2. And so it's kind of a hard picture to stare at because a lot of information is being thrown at us at once. It's pretty dynamic. But this is essentially all we're doing when we convert over for unit circle trigonometry into the xy plane. Any questions about the interesting animation? Okay, so our goal is just to get some terminology about what's happening with these functions. I've already mentioned that they're bounded, meaning they have an absolute max and absolute minimum, but they're also periodic. And usually in your study of algebra, these are probably the very first periodic functions you ran into. Periodic functions can describe all sorts of things, like anything that's a wave. They could be tides, they can be temperatures, and they're used in a whole bunch of interesting applications. The exciting frontier of applications to functions just like these is stuff like noise canceling headphones. The idea is sound is a wave, and if you find a wave that's opposite to it in the right sense, waves combine and can cancel each other out. So that's frontier research that's going on right now. We're getting pretty good at this stuff. But it starts here. Here's our chapter 6, periodic functions. And 6.1, we're looking into graphs of just two, sine and cosine. Then in section 6.2, we'll look at the other 4 trigonometric functions, tangent, cotangent, cosecant, and secant. First, we have to have a good working definition of what do we mean by periodic functions in the first place. That's the name of the chapter. All of our trig functions are periodic, so we need a good foundation of what it means. The idea is your function is periodic if it repeats. If there's some number p such that the function f at x plus p is the same as the function f of x. This is what we mean by periodic, just a repeating function. So in the graph below, you could think of this as your x. X is negative 15, and add the right number to it, you should get back to f of x. F of x is the output, negative 5. And if I add the right number, let's see, go all the way over here, all these outputs are different, until you get back up to here. It matches right at this point. Not only grab the maximum because it was an easy point to make, or to select and see it go over here, but I could have grabbed any point. This point here also repeats because it takes that value again at this spot and at this spot. And this curve, if it just keeps on repeating, it'll reach this height infinitely many times. So this is our first look at what we mean by periodic functions. They repeat not just once, but they repeat for all x in the domain of this function. And this is just a small set of the domain. You could imagine that if we had infinitely much paper and patience, the rest of the curve, this is freehand, so just be forgiving, would look like this. And it would keep on going in that direction forever. And same going off to the left. This is what our sine and cosine functions do. In fact, the function we're looking down here on the example is just a transformation of a sine function. So looking into this distance, we went from negative 15 all the way to positive 5 and repeated the maximum. It would repeat the maximum again somewhere over here. That tells us the period, let me get the right color to match this up. The period is p equals, we just want the distance between 5 and negative 15, so 5 minus negative 15 equals 20. So this is the minimum distance that you have to go for your values to repeat. And that's all we mean by a periodic function. Well, any questions, folks, with that first part of the definitions? Okay, because things are based on a circle and the circle just keeps on repeating over and over and over again, that's why we're expecting our functions to be periodic. Let me see if I have that graph any longer. There it is. Here's our periodic nature. It just keeps on reaching the same points over and over again. And what we're interested in is what is the period? What is the amplitude for these kinds of functions? So here's the next bit of information. All 6 trig functions are periodic, but their periods are not the same. So that's something that's interesting all on its own. Our goal is to say what are the periods of all 6 trigonometric functions, and that's going to assist us with graphing those functions, the major goal of this chapter. Now, the next thing we want to deal with is the amplitude of functions. A lot of people have a good working idea of what we mean when we say amplitude. By amplitude, we usually mean this. It's not the distance from a peak, say the maximum, and a trough, say the minimum. Instead, we imagine that this curve is just bouncing up and around some midline. Sometimes it's the x-axis, but sometimes it can be shifted over. This one seems to be oscillating or bouncing around is another word you could say. The midline, whose equation would be y equals negative 10, because it seems to be equally above and equally below, above half the time, below half the time. And then the distance from here to here equals, well, that looks like 5. That's what we would mean by the amplitude of the curve. Same if we went from here, the distance from the midline to the minimum would be distance 5 as well. So that would be our amplitude. But if you like formulas, if you're a formula person, this is the straightforward way to do it. It's nice to see it visually versus the formula. The amplitude is going to be the maximum value minus the minimum value, uppercase M minus lowercase m, divide by 2. So if we were to calculate that, we'll write M, that'll be our common shorthand for amplitude, equals the maximum value we obtain is -5, minus the minimum value obtained is -15. All those negatives make me uncomfortable, but we have -5 plus 15, so that's going to be 10. Divide by 2, giving us an amplitude of 5. And that's what we were seeing here when we said the distance is 5. This is equal to the amplitude. So those are the two fundamental things to know about our trig functions. All 6 trigonometric functions are periodic. This is how we calculate the amplitude when they have amplitudes. And here's the next interesting thing about this. Only sine and cosine have an amplitude. That's weird already. It turns out all other 4 trigonometric functions, they're not even bounded. So it's broken in a big way. You can't associate an amplitude to a function that does this, just shoots up. Yet they're still periodic. It's because they have vertical asymptotes where they just reset their graph between every single vertical asymptote. And they'll have infinitely many vertical asymptotes. So loads of information to talk about when it comes to trig functions. These are just the 2 core definitions. Our major goal is to start plotting them, and we're going to use the sine and cosine graphs as a launching point. Any questions at all, folks, with these 2 concepts here? Okay, so we can plot the functions in a lot of ways. If you're, say, using Desmos or an ordinary graphing calculator, you might plot it like this. Here is y equals cosine x. You might like the animation that we were playing from wikipedia.com, but this is kind of a friendlier picture. It's a little bit more static. Here's a sine function, and yeah, this is definitely periodic. We can just see it. The pattern's repeating. We hit the values 1 in a reasonable way. This is telling us that the period is 2 pi, and the distance from here to here is a distance of 1, so the amplitude is 1. But it's a pretty busy graph, and it's not too informative of how would you do this by hand if we did a transformation of cosine. And there's a lot of transformations we could give. We could say add, subtract units. We could add, subtract units from within the function, multiply by negative signs inside or outside the function, or rescale the function, multiply by a constant on the inside, multiply the variable by a constant. I said that backwards. Multiply by a constant on the outside for a vertical stretch, multiply by a constant inside for a vertical compression, depending on the size of the constants. Lots of things going on. Things that are highlighted in yellow are things that feel kind of backwards the first time you see this. Like, for example, a minus C means you're really going to the right, not the left. That's always something to kind of wrap your mind around. So to really get started in plotting all those things, we need just the basic function right here. This is going to be our launching pad for plotting any combination of sine. And there's a lot to observe here. We're just going to state the period and amplitude, so it's kind of like a formula page. But one thing we might do is just reconnect with what we know. Here is chapter 5 material. Good points for plotting sine might have been 0, pi over 2, pi, 3 pi over 2, and 2 pi, because we can calculate sine really rapidly on those values. We know the x and y coordinates exactly. So if we were at, say, angle measurement 0, that's why we're right here, right on the origin. We go up to pi over 2. This takes coordinates 0, 1, and that's where we hit the maximum, right up here. Notice something's missing for our x-axis. It doesn't tell us where the maximum occurs. We need to know that. We need to know that's pi over 2, and that's what we'll actually put on our sketch, not 0.51, 1.5. We want the x value that leads to the actual maximum, pi over 2 itself. So in other words, we're building our own scale here that's just more convenient for actually plotting these things. At pi, coordinates here go -1, 0, sine is the second coordinate. And so that's why we have intersection right at the x-axis again, exactly at pi. And that looks right. Pi is about 3.14 and some change, and it's just a little bit over to the right of 3. Next, at 3 pi over 2, coordinates here go, let me try again. Coordinates here go 0, -1. So that's why we're down here at our minimum value, -1. And this happens at 3 pi over 2. Finally, back over here, this coordinate we never put down, but we know it to be 1, 0. Matches over here. This is the periodicity. It's just repeating again. We take value 0 again at 2 pi. So this is our scale. We start from 0, go pi over 2 pi, all the way up to 2 pi. And if we kept on plotting, it's just going to repeat. This is the picture that we're seeing right here. We went up to 2 pi. Let me compress that down. And it just keeps on going again at 4 pi, same curve, and again at 6 pi, 8 pi, and so on. And same to the left. Here is -2 pi, +2 pi, 0 pi, and so on. So we wanted to state two things, period and amplitude. You can see from the graph that the minimum distance for the curve to repeat is 2 pi. I'll often write just P for period is 2 pi. The amplitude is the maximum minus the minimum divided by 2, or we could just say the distance from here to here. The amplitude is 1. And next interesting thing about this is to plot increment by 1/4 of the period, which is 1/4 of 2 pi, which is pi over 2 in this problem. Everything was just adding pi over 2 all over and over again. For example, this pi, if you didn't simplify it, is 2 pi over 2. Add 1/4 of the period, 1/4 p, to get to 3 pi over 2. Add again, we got to 2 pi, which is 4 pi over 2 if you didn't simplify it. And so this right here is something that we're going to emphasize a lot. Once you know the period of your sine or cosine function, you take 1/4 of the period, and this is going to take you to all of the interesting values, x-intersections, maximums, and minimums. So it's the same picture for the next one on cosine, but just a little bit different. Any questions at all, folks, for the sine graph building block? Okay, turning it over to cosine, here's what it looks like. Looks weird, right? But really it's the same thing. Let's go to Desmos and put in, well, this one was a cosine. With cosine, we're usually looking at a window that goes about like this. Oh, that's going to compress on me. Going to go from here all the way up to here, or you could just force this to work. 0 less than or equals x. Can't find the home rule. Let me try again. Less than or equals x, less than or equals to 2 pi. So we often take this as our view of the cosine function, only because we want to start at 0. And that insistence on starting at 0 means our shape's kind of unusual. But you might have noticed when it comes to cosine and sine, they look really similar. We put in y equals sine x on the top. The sine and the cosine function are just shifts of each other in a certain sense. That's just one sense at which this function is a cofunction to the one below. It's just a literal shift. Other than that, same exact function. But this is what we're usually plotting if we're doing some kind of transformation of cosine, a picture that looks about like this. This is the graph over one full period, and like before, the period to this is 2 pi. The amplitude is still the same at 1. And if we did this exercise one more time, I mean, we spent some time in chapter 5, we might as well make it worth our while. Here's the unit circle view of this. At 0, we have coordinates 1, 0. But just think, cosine is now the first coordinate, so that's why we started all the way up here at 1. At pi over 2, we are probably getting good at thinking cosine pi over 2 is 0. That's because the coordinates go to 0, 1 here. And here's that first intercept. This is directly at pi over 2. Then over here at pi, that's coordinate -1, 0. -1 is the minimum value cosine ever takes, so we're at the minimum part of the graph, and that would take us to pi. Or if you preferred, you could have called it 2 pi over 2, because all we're doing is starting at 0, adding pi over 2 to get to all the next interesting points. In fact, the next one, without thinking too hard, is go from 2 pi over 2, add the increment of pi over 2, now we're at 3 pi over 2. Check at the unit circle diagram, this is where we did all the work. 3 pi over 2 has coordinates 0, -1. Because the first coordinate is 0, that's why we expect to intersect on the x-axis again. Then it just repeats over and over again, all of those values, that's why it's periodic. But in particular, this value, we could also say is 2 pi. Add pi over 2 to this, that would be 4 pi over 2, or 2 pi. And that gave us the maximum value, 1 once again. So that's our quick view of cosine. And again, all the information's here, but what we're not doing is plotting cosine on its own. We're going to plot things like 3 cosine 4x minus pi plus 2, weird combinations. We want to know how much do we go to get to all the interesting points, just like on this graph. And the information is the same for both sine and cosine. The increment, the amount you need to add to, is going to be equal to 1/4 of the period, or 1/4 of the cycle, which just means 1/4 times p, which is 1/4 times 2 pi, which is the pi over 2 again. So this as a formula becomes extremely useful to us. It tells us essentially how to get to all the important features we're looking for on the graph. Well, any questions at the moment, folks, before we try actually graphing some of these?
Could you run me through that increment one last time? I'm not sure I understand how it's.
So the idea with this is that the full period from here, 0, to here, the 2 pi, is what we meant by period 2 pi. And it turns out the distance from here to here, that's where we started, and then we incremented to get to this next point right here. Essentially, what we're plotting is just these black points that we see here, 5 points each time, and then we're just drawing a curve right through. But this distance equals pi over 2, and it's the same distance each and every time. Distance equals pi over 2 here, and so on. I feel like I have to finish the diagram now that we started it one more time. Distance equals pi over 2 on this one. So if we take a period of 2 pi, divide it by 4, we're getting that value of pi over 2. We plot 1 point here, add pi over 2, we'll be at the x-axis. 2 pi over 2, or just pi after simplifying, that's the third point. We'll know we're at -1 if we're doing cosine, because it starts going down, reaches the bottom. Add pi over 2 again, we're at 3 pi over 2. We're back on the x-axis. Add pi over 2 again, and then we've reached the maximum value again. So that's what we mean by the increment. The distance will go to get to the next point.
Okay, that makes sense. Thank you.
Yeah, absolutely. Thanks for asking about that. So again, it's going to be our major technique. And for another document we haven't looked into yet, but we'll take a look at quite a lot, is this is just an overall summary of what to do for any one of these functions, so-called summary of plotting techniques. This is basically like a cookbook. It's a recipe of how are you going to plot sine, this transformation of it, sometimes called the sinusoidal function, or this transformation of cosine. We'd want to know the amplitude is the absolute value of whatever is here, This is in red because these are the only two functions with amplitude, so it stands out. The period is going to be 2 pi, just like in the graphs we were looking at. There it is, period is 2 pi on these. But if we put something right here on B, that's a transformation on the graph. It's going to compress it if B is greater than 1. And so you get the new period, 2 pi divided by B. And this is the part we were mentioning, the increment. This gets you to all interesting points on the graph. And then there's more. There's the phase shift we need to discuss, the fact that sometimes our curves move around, and they move around like this. We take cosine, let me go plus PS for phase shift, or just how about PH for phase shift? Dang it, we'll do H. And if we move H around, all it's going to do is move the graph around. So that's going to be what the phase shift is. Our goal is to take this information, kind of just a quick guide, the basic curve like we see right here for cosine, and the basic curve we see here for sine, and use them to plot these things. The sinusoidal function. It's kind of a weird word. I actually looked at that up today because it's been bothering me. Sinu just means sine. Oid, it just means like, so this is coming from Greek. And sinusoidal just literally would translate to sine-like function. So weird word, but it implies you're dealing with these two functions you're seeing here. These are like the building blocks for just about anything that's a wave. Some waves are really, really complicated, but depending on the amount of math you've taken, you can do crazy things like Fourier series to combine these in interesting ways to write out just about any periodic repeating pattern. So these are the major building blocks. We get a good handle on how to plot these, then all this leads into mathematical modeling, particularly statistics with time series. This is a rough guide on what we want to calculate to get this plot going. And this is just a reminder of what the period is and the amplitude is for both sine and cosine. I think we have enough time to go for one plot on this. And these instructions are pretty much verbatim from the homework set. So for each given function, we want to determine the amplitude, period, phase shift, and midline equation. So let's run through that information. The function we're plotting is this, -3 sine x minus pi. So that's an interesting combination of pi. First thing we want is the amplitude. And the formula tells us the amplitude is the absolute value of A, which is whatever is directly in front of the function. It's going to tell you how high it goes, how low it goes. Reason for that is whatever is in front of the function is this C value. That's just a vertical stretch or vertical compression. So that's how we're conflating that with what the amplitude is. So the number right in front, take its absolute value. Here it's going to be absolute value -3. We'll get a +3, and that's the amplitude in our function. One down. Now next, period. All right, P for period, but we might as well define these things here. So period, well, it's going to start with the period of the sine function or the cosine function. We're always just going to put that down to start, right out of the gate. And that might be the whole period, unless there's something in front. If there is a multiple scalar here, or constant, like 5 or pi, any other number other than 1, it's going to cause either a compression or a stretching, and that's affecting your period. Comparing to the plotting technique, sorry, I have too many things open. Comparing to what's going on over here, any number that is there, multiplying x is going to either compress or stretch, affecting the period. And the way it affects our period is this way. If we see a number right in front of x, we divide by that number. So that's how we're conflating these two. From the x is a 1, so our period is 2 pi this time. The other problems will be more interesting with a different period, but this is kind of like a warm-up one. Any questions with amplitude or period so far? Okay, so we got amplitude just because of the -3 there. Amplitude is always a positive number, so we just peel off the negative sign with the absolute value function. Because there's nothing in front of x, we just inherit the period from sine x and cosine x of 2 pi. If there was a 5x here, we would have divided by 5 immediately. Something else does happen. There's a minus pi, and that's going to be a phase shift. And I'll often write PS, just a shorthand for phase shift in these notes. So PS for phase shift. The idea is any number that's here gives you a phase shift like this. You go from the negative sign to something positive. If it was a positive here, we'd put in the negative sign. And if there's a number in front, you have to divide by that number both into the period and into the phase shift all at once. But for us, the phase shift is just going to be equal to positive pi. Easiest thing to forget is you have to change the sign here. Phase shift is telling us where the graph is going to start. It's moved to the right by pi. And that's connecting, sorry, wrong window again. That's connecting this information over here. We shift right by going a negative. We shift left by going a positive constant. So these are just horizontal translations. In the land of trigonometry plotting, we call those phase shifts. So those are the 3 ingredients we would like. The midline equation is the line y equals d, but d is just the number being added or subtracted, and there is no such number. So we would just say midline, negative pi here. Midline is the equation y equals 0. So now we're ready to plot, but we still needed one extra thing. The increment is 1/4 of the period, which is 1/4 of 2 pi, which again on this problem and the others we looked at is pi over 2. Yeah, go ahead.
And on pi annotation.
Oh, thanks for spotting that.
When you were backtracking, cut off the bottom.
Yeah, and I kept like a negative sign in there. Thanks for spotting that. So yeah, don't forget to change the sign on that. You know, that's some good highlighting right here. It turns out this is the minimum set of information you need for a nice plot. So here's how it's going to come together. First thing we put in is information on the amplitude. That's y-coordinate information or y-axis information. Next thing we do is, because the phase shift is pi, this is where we start. Period is 2 pi, so we're going to end at 3 pi. We're just adding 2 pi to this. So this would be pi over 2. This would be pi where we start, or 2 pi over 2 if you prefer fractions. We're adding pi over 2 to these to increment. So next one's going to be 3 pi over 2, 4 pi over 2, 5 pi over 2. And we're always going for 6 points. 6 pi over 2, and it's weird to leave these unsimplified, but I'll do it this time on this just to emphasize if it's helpful, you can just leave it like that. And here's what the sine function does. Sine, wherever it starts, always starts at the x-axis. So see the graph above. We have another interesting bit of information where it says, because of this, there's a reflection on the x-axis. Looking at a transformation of graph information, if you put a negative sign right there, you reflect across the x-axis. And that just means our sine function isn't going up, it's going down. So on the next point, it hits a minimum, then it rebounds back to the x-axis. On the next point, it hits the maximum, then it comes back down on the x-axis, and this is our whole graph. So the thing that we needed in the back of our mind was y equals sine x has this basic shape. But if you put a negative in front of it, y equals negative sine x, the shape changes. It goes like this instead, reflecting across the x-axis. Let me fix that arrow. So a lot of things going on at once. The strategy is get your amplitude. It tells you the scale on the vertical axis. Get your period, and you just want 1/4 of it. That's going to give you the increment, which tells you all of the interesting dots that you're going to put down, leading to x-intercepts, as well as the maximum and minimum values. And you notice that that hits the instructions just right. Our sketch has to have the exact values on the x-axis, y-axis, and here they are. They go pi if it's reduced, 3 pi over 2. This one goes 3 pi over 2, 4 pi over 2, so 2 pi, 5 pi over 2, and then 3 pi when you reduce them. It has the maximum and minimum values of f. We didn't write them as coordinates, but we can observe them. At 5 pi over 2, we have the maximum value of 3. At 3 pi over 2, we have the minimum value of -3. So that's what we will be practicing on the next couple problems when we come back on Wednesday. But any last questions, folks, on where the notes are going so far? Okay, sorry for running over about a half a minute. When we come back, we'll just do a couple more interesting examples. This one looks like it's kind of nasty, and nastier still, lots going on with these. This will get us set up for the homework set. And we'll look at this one right here, seeing what this is all going for. One great application is curve fitting. That's how we'll see how plotting these sinusoidal functions actually fit into this kind of task. But that's all I have for you folks today. We'll try this out again on Wednesday and probably take a look into what's going on in section 6.2 after we finish this one. But have a great night, folks. I'll see you all on Wednesday's class. Thanks.
Thank you.
You too. Have a good one. And this is the point of class where people typically just disappear by converting files over. Does it feel like the magic has been dispelled? That's good to hear.
Well, I have to decide, do I wanna go back to living the magic, or do I wanna actually just come in? I feel like coming into class would be very helpful if I'm stuck on stuff like this.
Yeah. I think if I was a student during the time of Zoom being available, I think there would have been some classes where it would have been harder for me because I think I'm just more distracted.
Yeah.
Working from home, even if I close my door and try to minimize distractions, I still have other tabs open on my Zoom
Yeah.
computer, stuff like that's gonna distract me like crazy probably.
Yeah, that's very easy.
But I assume Zoom classes have been out for a while, so probably people have strategies against